Hi all. So today we're going to talk about exercise 4.16, angled rails. And this question is about two particles of mass m constrained to move along two horizontal frictionless rails that make an angle 2 theta with respect to each other. So it basically means that these two mass, so this mass and this mass, they can only move along the rails. And then they are connected via a spring and they kind of oscillate up and down, or rather up the rail and down the rail, and that's how they oscillate. So I also drew another pair here. So this is what it will look like when it fell here. So as always, when we encounter a mechanics problem, we can always try to analyze the forces a bit. So let's look at only one of the side first because they're quite symmetric to set up. So for this mass, we have gravity, we have normal force, and we have spring force. And then for this mass here, we have gravity, normal force, and this time spring force is pointing outwards. And so let's see. Gravity is constantly trying to pull this mass downwards along the slope, along the rail. And it is the spring force that is bringing this mass back up. And normal force doesn't really contribute because normal force really depends on the net force a lot on this side. So all normal force is doing is preventing the speed from going elsewhere. Say going to say flying off this rail. Like normal force is preventing the mass from flying off the rail. So for example, if we look at the bead here, the mass here. So if we have the rail, we have the mass, and then gravity is pointing downwards, and normal force that way, and then you have the spring force. So we can decompose gravity into this component and this component. So we call that G perpendicular and G parallel, and ignore this. So this is G perpendicular, and it is directly opposite to the normal force. And so that is normal force's responsibility, or what the normal force is doing. And same thing with the spring force also. So spring force we can decompose into upwards, uh, up the rail, and we can create another component of opposite to the normal force. So that'd be F as perpendicular, F as parallel. So all normal force is doing is to balance out the sum of these two forces. So it really isn't doing any net force, it's just canceling them out. And that's why we say normal force isn't really making this mass go up. It is the spring force. At this point, it is the spring force that is making the mass go up. And at this point, it is the spring force and the gravity that's trying to pull the bead back down. So let's try to find the spring force. So our general logic right now is to decompose all forces, or to decompose all spring force and gravity into perpendicular, so perpendicular to the rail and parallel to the rail. And then by doing this, we will find the restoring force. And from there, we can find a formula to allow us to get the frequency of this motion. So let's try to do that. So why don't we call this length L? So from the mass to the bottom, so L, and then we can call this L2, since they are always parallel, as indicated by the question. So we just need the length of the spring here and here. So how can we do that? Well, we can do it using the cosine rule, right? Because we know that this is an equilateral triangle. So then if we call the length here x, then we know that x equals to square root L squared plus L squared plus 2L times L cosine 2 theta, which is equals to 2L squared. Oh, sorry, it's minus here. So L squared plus L squared minus 2L times L cosine 2 theta. So it's 2L squared minus 2L squared cosine 2 theta. And then from the formula, we know that cosine 2 theta equals to cosine squared theta minus sine squared theta. So then we have x equals to square root 2l squared minus 2l squared bracket cosine squared theta minus sine squared theta. And then we have x is equal to, so if we factor out the 2l squared, we have 2l squared, 1 minus cosine squared theta plus sine squared theta. And then we know from the identity that sine squared theta plus cosine squared theta is 1, so 1 minus cosine squared theta is sine squared theta. So we know that x equals to square root 2l squared 2 sine squared theta. Because this is sine squared theta to sine squared theta, we get 2 sine squared theta. And then so x is equals to square root 4l squared sine squared theta. And we can make it out, so it's basically 2l sine theta is x. Next, we can write out the spring force. So the spring force is basically Fs equals to kx, which is 2kl sine theta. And so that is our spring force. Next, we're trying to find the component of the spring force along the rail. So that is what we're trying to do. So we're trying to find the components along the rail for all of the forces, which is gravity and spring force. So let me just draw the diagram again here. So we have a mass here, we have a mass here, and then we have a spring connecting them, and then this is 2 theta, and then we know that spring force at this point, let's say it goes this way. So we're trying to decompose it into parallel along the rail and perpendicular to the rail. So, and this is 9 degrees. So why don't we call this angle phi? So then we know that Fs parallel equals to Fs cosine phi. And then how can we find phi? So why don't we draw a bisector of this angle, 2 theta. So then now we have theta here. And now we know this is a right triangle because this is an equilateral triangle. And then so we know that if this is theta, this is 90 degrees, this must be 90 minus degree theta. And then so phi should be equals to 90 minus theta. Why? Well, because we have a line here that are intersecting, and we know that this angle is equal to this angle always. And that's why we know that phi is 90 minus theta. And so Fs parallel equals to Fs cosine 90 minus theta. And then we know that cosine 90 minus theta is basically sine theta, so we know it's Fs sine theta. And then we know that Fs is 2kl sine theta, and so we know that Fs parallel is 2kl sine squared theta. And so this is the parallel component. And for gravity, we're trying to find the parallel component. Well, we don't really need to because we're only trying to find the angular frequency. For gravity, we know it's definitely a constant. Definitely a constant. And so what this does is basically shifts the equilibrium position a bit downwards, but it doesn't really affect the oscillatory motion, or it doesn't really affect the frequency. So this is also the reason why, say we have a block like this, and it's oscillating back and forth, and we also have a block like this, and then back and forth, same spring constant, same mass, they have the same frequency. Why? Well, because only the restoring force matters. It's only the restoring force that really determines the angular frequency, because angular frequency is the square root k over m, and that k basically comes from the restoring force. And that's why we don't really need to worry about G power. So we only have this as the restoring force. And then from here, let me write it in a more familiar form. So we're familiar with the form kx. We need the k. Well, x here is not the same x, but this is basically the variable. We just need a variable here. So we had 2kl sine squared theta. What is the variable here? It is L, right? So we have 2k sine squared theta. And then we have an L here. This is the only restoring force in the system. And so now we basically know. So isn't this formula equivalent to the form of kx? Except that this time k becomes 2k sine squared theta. And then L and x are just variables. And so we know that the effective spring constant, k, equals to 2k sine squared theta. And so we know that omega equals to square root. So effective spring constant, we do ke. So then it's equals to square root ke over m. And so it is square root 2k sine squared theta over m, which is square root 2k over m, and then we can bring the sine squared theta out of the square root, and we get sine theta. So the answer is omega equals to square root 2k over m times sine theta. And that is our answer to this question. Thank you for watching, and I wish you a Happy New Year.